Welcome back to Physics 151 online. As you work through physics problems this semester, there's a few things that you should remember. They're not always going to be easy, and you won't necessarily know exactly how to solve them the first time that you look at them. And here's a saying that was written in the foreword of my freshman year physics book. Problems worthy of attack prove their worth by hitting back. So, the moral of the story is that learning physics is a little bit like an athletic training endeavor. It involves resistance training. We do a problem, we solve it, we do a little bit harder problem, we solve that one, and then eventually we get better and better at solving problems of all different types. Also, on a little more humorous note, even NFL players need to brush up on physics. Here's a picture, a little bit dated now, of Mike Vick reading a book entitled Quantum Physics in Short Yardage Situations. Something to keep in mind as the NFL season begins shortly. Okay, in Chapter 3, we're going to extend our discussion of motion to cases where there's more than one direction involved. For example, a golf ball or a soccer ball flying through the air is moving in at least two, and depending on the true nature of its path, maybe even 3 dimensions. So we're going to look at position, velocity, and acceleration and their connections in vector form, involving not just 1 dimension, but 2 and even 3 dimensions. And so that will culminate in our treatment of projectile motion, which is a special case of 2-dimensional motion with constant acceleration. Then we'll go on and talk briefly about non-constant acceleration, and eventually finish up Chapter 3 with an introductory treatment of acceleration in circular motion problems. So first of all, now that we explicitly have to write down position, velocity, and acceleration as vectors, we'd better talk through the notation for doing that. We're going to use unit vector notation so that the general position vector describing where an object is in the coordinate system will be indicated by the vector r, which will have x, y, and z coordinates. And these x, y, and z coordinates can quite often be quantities that are changing in time. So just because it says x doesn't necessarily mean that it's just a single value x. It might be changing with time. Of course, the velocity vector is the derivative of the position vector, and so if we differentiate this position vector, what we're really doing is differentiating each term in turn, so that dr dt is the derivative of x with respect to t, we call that vx, times I hat, the derivative of y with respect to t, which is v sub y, times j hat, plus the derivative of z with respect to t, we call that v sub z, times k hat. And what you'll notice is that each of these terms has in it a derivative with respect to one of the coordinates. And as I just read off when I was describing this velocity vector notation, each of the velocity components is one of these derivatives. Now, if we move on to deal with acceleration, in much the same way as velocity is the derivative of the position vector, the acceleration vector is the derivative of the velocity vector. It will have 3 components as well, and each of these acceleration components is the derivative of a particular velocity component with respect to time. Alright, so this should look fairly straightforward. We're just generalizing all of the equations for 1-dimensional motion to now apply along not just a single direction, but all 3, the x, the y, and the z directions. Now what about motion with constant acceleration? Are there similar formulas to the ones that we derived for 1-dimensional motion that we can use for 2- and 3-dimensional motion? And the answer, of course, is yes. They just look a little bit different. So the general way of deriving these starts off with the vector equation a equals dv dt. If we cross multiply and then integrate both sides, we end up with the integral of the change in velocity vector evaluated between the initial velocity vector and the final, and then the integral of the acceleration vector dt from t equals 0 to a final time t. If the acceleration is constant, right, then the left-hand side of this equation, simply that's just v minus v0, that's easy, but then the right-hand side becomes simple as well, because the acceleration can come outside the integral if it doesn't depend on time, leaving behind a integral dt from 0 to t, or just a times t. So this equation, v minus v0 equals at, we've seen that before, but now it's a vector equation. And as such, it contains within it components along x, y, and z. So let's just assume that we have a two-dimensional situation, because it'll save a little bit of the writing. If we had a third-dimensional component involved in this problem, then we would simply have a k term as well as the I and the j terms. But to keep it simple, let's just see where this comes from, right? The velocity vector on the left-hand side can be written as vxi plus vyj. The initial velocity vector, v0, can be written as v0xi plus v0yj, and then the acceleration vector has components along the I and j directions as well. And so what we really have is a different way of writing this vector equation, explicitly showing the components along the I and the j directions. Now, although this is a single equation, what we find in any kind of vector equation is if two vectors are equal to one another, the only way that can be true is if their components are also equal to one another. And so a vector equation like this that has two components in it immediately implies two different equalities, one for the x direction and one for the y direction. So let's just gather all of the terms that are along the x direction, all of the terms with I hat, and write them down in a single equation. Notice at this point we've dropped any of the vector notation. All of these three are the terms along the I hat directions, and they must be equal to one another. So we can do the same thing also for the y direction, and we see that these two equations, they're identical equations, but one pertains to the x direction, one to the y direction. So what was a single equation involving a vector has now become two equations involving the components of the vectors, and they're both important. One more integration step, and I won't show all the details here, but if we now go from velocity to position, we can see that we will derive similar equations for the change in x and for the change in y as a function of time. Both of these equations should look very familiar. The one on the left, apart from the x subscript, looks identical to what we worked on in Chapter 2 for constant acceleration motion. The only difference now is we put the x in there explicitly to remind us that this is the component of v0 along the x direction, and here we have the x component of the acceleration. So now we've got two equations involving velocity and acceleration in time. We've got two equations involving displacement, initial velocity, acceleration, and time, and then we can combine these two equations in various ways to derive the other equations for constant acceleration motion. And I'll just show one of them, right? If we were to solve for time in the top equation and substitute into the second equation and gather the terms and simplify, we would get this familiar looking expression for the difference in the squares of the velocity components. And the same thing would happen along the y direction. And so what I want you to see is, even though now we're dealing with two-dimensional motion, the equations are still the same equations if the acceleration is constant. It's just that there's twice as many, because there's one for the x direction and for the y direction. But please don't think of these as some new kind of physics. All they really represent is twice as many equations of the same type that we've already become familiar with. So we can use the same kind of combinations to derive the other two constant acceleration motion equations, but I won't show them right here. Alright, we'll finish up with a simple example that just presents the kind of problem that you might see on your homework. So an object is at the origin at time t equals 0 with an initial velocity given by this vector here. Alright, so we have an I component and a j component in units of meters per second. And we might be told that it moves with constant acceleration, which is the hint that we can use those equations that we've just discussed. And a short time later, at t equals 3 seconds, its velocity has changed and is now measured to be this value. All right, they're still vectors, but you can see that they're not the same, and they've changed. The object has changed its velocity direction, and it's also changed the magnitude. And so a simple homework problem might ask us to find the acceleration vector for that object during that time, and then to go beyond that to find an expression for the object's position vector at any time. And we can quite straightforwardly use those equations for constant acceleration motion along the x and the y direction in order to answer these two questions. I won't work out the solution here, but it's a typical homework type problem. Now let me just finish with the application of these equations to the special case of projectile motion. So near the Earth's surface, if an object is launched and then is only under the influence of the Earth pulling down on it, then it will experience the familiar vertical acceleration downward towards the Earth's surface, and unless there's some kind of air resistance or wind involved, there won't be any horizontal acceleration. And so the two acceleration components that we can then plug into the constant acceleration motion equations look like this. And they actually simplify things quite a bit. So for example, the kinematic equation for the x component of velocity looks like this. And if the acceleration along the x direction is 0, what this tells us is that the x component of the velocity is equal to the initial x component of velocity, so that it never changes. All right, along the y direction, it's not quite as trivial, because here the acceleration along the y direction is negative g, so we plug in negative g, and we see that v sub y is v0y minus gt. So these become the two equations for constant acceleration motion when we have projectile motion, and so on. So we can then also plug in a sub x equals 0 and a sub y equals negative g into the other equations for constant acceleration motion. And I'll just caution that it's very, very important to use the correct subscript notation for each of these terms. For example, we're not going to be writing down just v0 anymore. We're only going to write down the components of v0 along the x and the y directions in these equations. If you leave off the y and you leave off the x, you might confuse yourself into thinking that two quantities are the same, when in fact these two quantities are quite different from one another. It's crucial to distinguish x and y components of position, velocity, and acceleration to solve the kind of physics problems that we'll be attempting in this part of the course. Okay, so this gives you an overview, and hopefully it will help you prepare for class, where we will work out some examples using these equations. I will see you in class.